Hello, everyone. Today I'm presenting my paper on biometric authentication using enhanced remote photoplethysmography signal morphology. This research was conducted at the University of Oulu and Zhejiang University. First, let's introduce remote photoplethysmography, abbreviated as rPPG. rPPG tracks blood volume variations that cause subtle skin color changes in facial videos, as seen in the left video, which demonstrates facial color magnification. This amplified color change corresponds to each heartbeat. To measure the rPPG signal, refer to the middle figure. Here, ambient light and a camera capture facial video. Light hitting the skin undergoes specular and diffuse reflections, but only the diffuse reflection reveals blood volume changes. By tracking these facial color changes, we can measure the rPPG signal. PPG-based biometrics have been extensively explored in research, using morphological features of the PPG signal. By employing contact sensors like pulse oximeters or smartwatches, we can record these PPG signals. As shown in the right figure, there are distinct morphological features within the PPG signal that are highly useful for identifying individuals. This method has been validated for person authentication in earlier studies, which inspired our work to use the rPPG signal, captured by a camera, to achieve a similar goal. By analyzing rPPG signal morphology, we aim to identify different individuals, which is the motivation behind this work. Let's explore the advantages of rPPG biometrics. Firstly, the rPPG signal can be extracted from de-identified videos, enhancing privacy protection. As seen in the first figure, which displays a de-identified video, we can apply pixel permutation for identification without heavily relying on visual information. The rPPG signal remains intact in such videos. Secondly, since rPPG is extracted from visual videos, it can be combined with face recognition, improving the accuracy of traditional face recognition systems. This integration enhances security as the rPPG signal is more secure and harder to manipulate than visual data. Lastly, rPPG is non-contact and uses off-the-shelf cameras. This means existing face recognition devices don't require hardware modifications. We can easily integrate rPPG into these systems to boost accuracy and security. I'll provide a brief overview of the rPPG authentication framework. First, we start with a facial video, which we then convert into a de-identified format, removing any visual identifiers. Next, our rPPG model extracts the rPPG signal from these anonymized videos. We then isolate periodic segments from the rPPG signal, corresponding to each heartbeat. Every heartbeat contains distinct morphological features vital for our person authentication process. Finally, the rPPG authentication model outputs the authentication decision based on these morphological characteristics. Let's dive into the pre-processing steps for face authentication. The primary goal here is to ensure our biometric model uses only the rPPG signal, extracting valuable spatial information while maintaining privacy. This approach safeguards visual data during the authentication process. First, we average and downsample frames from facial videos to create a downsampled video. We then apply pixel permutation, removing identifiable facial features. Next, we transform this video into a spatial temporal map. From here on, we use only this map for rPPG extraction and authentication, ensuring that no facial information is used, thus preserving privacy. Let's discuss the first training stage, rPPG unsupervised pre-training. Our aim here is to shape a basic rPPG model capable of extracting heartbeats. The beauty of unsupervised training is that it doesn't rely on ground truth rPPG signals from contact sensors, meaning we can use facial videos without subject IDs. On the left, you can see a figure illustrating our use of a contrastive learning approach for this unsupervised training. We feed the spatial temporal map into the rPPG model. Using random patch sampling, we extract various views from the rPPG feature map. We then group samples from the same video and separate those from different videos. After this contrastive training, we move on to the inference stage. Here, the model outputs the rPPG signal, visualized in the figure below. The heartbeats align, shown in orange, but the morphological features in blue need refinement. This brings us to our next training stage, where we'll hone in on the rPPG signal's morphological features. I'll introduce the second training stage, which is the hybrid training approach that combines rPPG with contact PPG, abbreviated as cPPG. First, let's dive into the rPPG branch. We capture a video and convert it into a spatial temporal map. Using an rPPG model, we generate and segment the rPPG signal, focusing on periodic segments. From there, a morphology model helps us understand each segment's unique characteristics, leading to precise identity predictions through cross-entropy loss. Switching to the cPPG branch, we incorporate an external dataset to enrich our training diversity, as rPPG data alone can be limiting. We process the SPPG signal similarly, segmenting and analyzing it with the morphology model. This dual approach, trained through alternate backpropagation, allows our morphology model to excel in extracting meaningful features for accurate identification. Through this hybrid method, we harness the strengths of both rPPG and cPPG dataset to improve rPPG biometric performance. On this slide, we'll delve into the results of our rPPG authentication method, evaluated using the equal error rate and area under the curve metrics on OBF, UBFC rPPG, and pure datasets. Firstly, we found that a longer signal duration enhances performance. This makes sense as more heartbeats provide richer information, helping to filter out noise and irregularities, thereby boosting overall accuracy. Secondly, intra-session analysis consistently yields strong results. This is likely because the model is trained and tested within the same session, reducing variables. Thirdly, the cross-session results, comparing pre- and post-exercise in OBF, show only a minor performance decline. This indicates that rPPG biometrics are relatively resilient to changes in heart rate. Lastly, cross-session analysis on the pure dataset, which involves static-to-face motion scenarios, reveals performance degradation. This suggests that rPPG biometrics are sensitive to facial movements. This table compares the performance of different biometric methods. First, this table demonstrates that our proposed method, combining rPPG and cPPG training, outperforms training with rPPG alone. This is reasonable, as cPPG enhances training diversity, whereas rPPG-only training is limited to rPPG data. Second, rPPG biometrics show superior performance in face recognition on de-identified faces. This aligns with expectations, as face recognition heavily depends on facial appearance, which rPPG biometrics do not rely on. This underscores the benefits of rPPG biometrics for privacy protection. Third, rPPG biometrics achieve competitive results compared to cPG. Despite potential noise in rPPG signals, the comparable outcomes indicate that rPPG is highly promising for practical applications. In this slide, I'll provide visualizations of rPPG morphologies. First, the left figure displays rPPG morphology figures for different subjects, ranging from subject A to subject H. We observe that rPPG morphological features vary significantly between individuals. For instance, the systolic peaks, dichrotic notches, and onsets and offsets differ, resulting in distinct overall contours. On the right, we illustrate the impact of motion on these morphological features. In the first row, representing a steady state, the rPPG morphology is very clear. In the second row, with motion, we notice additional noise affecting the overall morphology. This suggests that rPPG biometrics could be sensitive to motion, potentially distorting morphological curves. However, in practical applications, people are often in relatively steady states, so this shouldn't pose a significant issue for the use of rPPG biometrics in real-world scenarios. Finally, we present our overall conclusions. First, we validated the feasibility of rPPG biometrics using facial videos. Second, we introduced a two-stage training scheme along with a novel cPG-rPPG hybrid training method. By incorporating external cPPG biometric datasets, we enhanced rPPG biometric authentication performance. Lastly, our method leverages de-identified facial videos for authentication, effectively protecting sensitive facial appearance information. Thank you for your attention. We look forward to your questions and feedback.